Good day and welcome back. This is part one of our discussion of double integrals in polar coordinates. Towards the end of Calculus 2, we spend a bit of time introducing the concept of polar coordinates and see that they are highly conducive for describing circular regions which are typically symmetric about the origin. And this section will investigate, for such a region D, how we can conveniently and sometimes very efficiently evaluate the double integral using polar coordinates. So to start, let me give you kind of the reminder and maybe part of our motivation of why we are dealing with double integrals is because they can be interpreted geometrically as an enclosed volume. And remember, there's maybe a bit more to saying kind of an enclosed volume. We'll put quote unquote here. We're really thinking kind of this idea of a net difference of volumes. Volume enclosed above the z equals 0 plane, subtract away volume enclosed below. Now, to reintroduce polar coordinates, let's kind of go back to the basics. If we start off with a point, say its coordinates are x comma y. What the x and the y represent is kind of this, what we might think of as a directed distance from the x and the y axes, respectively. So if we trace down from the point to this horizontal axis, that's the distance y. And if we trace from our point over to the y-axis, that measures the distance x. In polar coordinates, we are going to view this slightly differently. We are going to think of the point having the form r comma theta, where r is a typically positive constant representing how far you are away from the origin, and theta is an angle formed coming up from the positive horizontal axes up to our point. And a few kind of reminders. The typical formulas we have associated to polar coordinates that we can get directly from our right triangle that we have drawn is that x is equal to r cosine theta, y is equal to r sine theta, and x squared plus y squared is r squared. And I should also mention kind of the built-in restrictions that we impose on r and theta. The typical convention is that we think of r as being bigger than or equal to 0, and theta as being in this interval from 0 to 2 pi. And I'll also add the disclaimer that sometimes it's more convenient to think of negative theta values, which would correspond to rotating from that positive horizontal axis in the clockwise direction. So let's go ahead and think about applying polar coordinates to a few common examples. To the left, we have a disk D, which is a circle centered at the origin, radius 3, and everything inside of it. Let's see if we can describe this in polar coordinates. And the key observation to recall from Calculus 2 is that this outside circle is represented by r equals 3. And note in general, if r is equal to a constant, that represents a circle of that radius centered at the origin. So in our case, r is going to vary from being 0 up till we hit that circle. So that is to say the r values are between 0 and 3, and we're going all the way around. So the theta values would be between 0 and 2 pi. So in terms of polar coordinates, this is a highly convenient region to describe. The r values and the theta values are both just varying between numbers. And note, you could similarly have something that's more of this kind of annular region, something between two circles. So the outside circle, we're thinking of it as having radius 2. The inside circle, we're thinking of it as having radius 1. And note, going along this positive horizontal axis, that corresponds to theta being 0. And going along this vertical positive axis, that corresponds to theta equaling pi over 2. So if we wanted to describe this region in polar coordinates, we can note the r values lie between 1 and 2, and the theta values lie between 0 and pi over 2. So once again, in terms of polar coordinates, these are extremely convenient regions to deal with, because these variables, r and theta, are only varying between constants. In fact, they may not look like it, but these are regions that we would refer to as being a polar rectangle, where a polar rectangle is a region of the form that's called R, which is made up of polar points, r and theta, where the r values vary between a and b, which are constants, and the theta values similarly vary between constants. Let's call them alpha and beta. And if we look above, these are two perfectly good examples of polar rectangles. So for example, a is 1, b is 2, alpha is 0, beta is pi over 2. A very kind of generic representation of this, if we were thinking of a polar rectangle, it's going to look roughly like this. And how we can see this polar rectangle is you have maybe the bottom portion corresponding to a theta value of alpha, this upper slash left portion corresponding to theta equals beta, and then if we continue on the outside, we're thinking r equals a, r equals b. And this is a polar rectangle. So even though it may not look rectangular, right, this is a circle actually, they are polar rectangles because of how the r and the theta values are bounded between constants. And it turns out that, much like we experienced with Cartesian coordinates, double integrals over rectangles are the ideal scenario for us to work with. So let's think about how that would work in polar coordinates. So the following property is going to indicate to us how we can evaluate a double integral over a polar rectangle. So if we have a polar rectangle, which is given by having r values between a and b, where they are positive, and theta values between alpha and beta, with the stipulation that that range of theta values is not exceeding 2 pi. So let's go ahead and write out now what this double integral would be in polar coordinates. And if we were going to convert this into polar coordinates, we need to change each of our variables accordingly. So it turns out each x needs to become an r cosine theta, and each y needs to become an r sine theta. So this will be the double integral. Limits of integration are going to be added in. Each x becomes an r cosine theta. Each y becomes an r sine theta. And now the new part, which is in no way obvious, is that we have to rewrite this dA. And it turns out that in polar coordinates, the dA is going to become r dr d theta. So that is to say, we've introduced this new r that has to be part of our integrand. So dA is r dr d theta. And in terms of limits of integration, on the inside, we have our r values varying from a to b. And on the outside, we have our theta values varying from alpha to beta. And what I'd like to do now is give you a bit of intuition as to where this r comes from without really going through too many of the details. Just enough to get that intuition that the r value kind of makes sense, and then I'll throw out there the idea that we are going to revisit this. This is something that we are going to see in section 15.9, and we will see in section 15.9 very precisely from a computational perspective exactly where that r comes from. But for now, I'm going to give you just a little bit of intuition so that it makes sense to use this formula, as we will be using it an awful lot. And to give you a bit of intuition, what we will do is go back to the method we used when we introduced a double integral over a rectangle in Cartesian coordinates. The idea there was to take our starting rectangle, now it's a polar rectangle, and break it up into a bunch of little subrectangles. And in order to do so, we will take our range of theta values and break it up into a bunch of little subintervals of width delta theta. And similarly, we break up our range of r values into a bunch of little subintervals of width delta r. And what that's going to do is it's going to put a polar grid on our polar rectangle. And I'm not going to attempt to draw this and make the picture look more complicated than it needs to be, but you could certainly look in the textbook for an associated picture. Now, what we want to think about is for this kind of generic subrectangle, what would its area be? Because remember, the dA term is really kind of this small area element. What is the area of one of these little subrectangles? So let me draw a blown up version of this little subrectangle, which we see to the right. We're thinking how the theta values vary on one of these little subrectangles. Is it measured by the width that we broke the theta intervals up into, delta theta? And similarly, kind of the width in terms of the r values comes from this delta r. So the length here would be change in r. Also, we have to pick some sample point typically in this generic rectangle. So I'm going to go ahead and just say this upper left point that we see, I'll call this r sub I theta sub j. And all I'm doing is just trying to introduce enough to write down a formula for maybe what this length would be. And note, if we think back to how we find the length of a portion of a circle, the circumference is 2 pi times the radius, because the radius is how far it is away from the origin, and 2 pi is kind of the range of theta values you go through. Putting that into play, we would say that the length of this outside portion would be r sub I, how far you are away from the origin, multiplied by delta theta, that range of theta values that we go through. And this shows us everything that we need to know. So thinking back to our previous discussion on double integrals over Cartesian rectangles, when we write down the Riemann sum, there's this quantity delta A, which represents the area of one of the small subrectangles. So in this case, it's going to represent the area of this small generic polar subrectangle. And instead of trying to write it down exactly, we will instead approximate the area of this subrectangle as its length times its width. Just multiply together those side lengths. So we could think of this as being r sub I delta theta delta r. And the key observation to note is that if we go from our delta A to our dA, what we would get back is r d theta dr, where the order of the d theta and the dr here is somewhat irrelevant. But the key observation is that this r sub I is corresponding to the r that appears in our formula for polar coordinates. So without going into too many details, hopefully that gives you a little bit of intuition as to where such a formula comes from. If you're unsatisfied with that explanation, you can look in the textbook and they explain it, but hold off also to 15.9, and we will see a very precise reason and a quantitative calculation as to where that r comes from. In our next few videos, we will put this new formula to use. So stay tuned and take care.